Hello everyone and welcome to Dr. Carminati's YouTube channel. I'm so excited to have you here today as we dive into a groundbreaking topic. How can the GKP approach to tackling optical loss in photonic quantum computers be the future of scalable quantum technology? Suppose you're as fascinated by the potential of quantum computing as I am. In that case, I'd love for you to share your thoughts in the comments, suggest ideas for future videos, give this video a like, and hit that subscribe button to join our community of curious minds. Let's explore this cutting-edge science together and discover how it might shape the future of technology. What is quantum computing, and why photonic systems? Let's dive into the world of quantum computing and explore how the Gottesman-Kitaev-Preskill (GKP) approach addresses one of its biggest challenges: optical loss in photonic systems. Quantum computing promises to revolutionize how we solve complex problems. Unlike classical computers, which use bits to represent information as either 0 or 1, quantum computers use quantum bits, or qubits. Qubits can exist in a combination of 0 and 1 simultaneously, thanks to a property called superposition. This ability allows quantum computers to perform many calculations simultaneously, potentially solving problems like simulating molecules for drug discovery or optimizing global logistics that would take classical computers millions of years. Photonic quantum computers, which use light particles called photons as qubits, offer a promising path to building scalable quantum systems. Photons bring several advantages. They travel through fiber optic cables with minimal loss, making them ideal for networking. They also operate at room temperature, unlike other quantum systems that require ultra-cold environments near absolute zero. Additionally, manufacturers can integrate photonic components onto chips, much like the ones in your smartphone, enabling mass production. These benefits make photonics a leading contender for creating large-scale quantum computers. However, photonic systems face a significant challenge: optical loss. When photons travel through fibers or interact with components, some get absorbed or scattered, introducing errors. These errors disrupt the delicate quantum states needed for computation, making it hard to achieve fault tolerance, the ability to correct mistakes and run reliable algorithms. The GKP approach, named after researchers Daniel Gottesman, Alexei Kitaev, and John Preskill, tackles this problem head-on, offering a pathway to scalable quantum technology. Let's explore how it works and why it could define the future. Understanding optical loss in photonic quantum computers. Optical loss occurs when photons, the carriers of quantum information in photonic systems, fail to reach their destination. Imagine sending a letter through the mail, but it gets lost before arriving. Your message never makes it. In a photonic quantum computer, photons travel through fiber optic cables, pass through beam splitters, and interact with detectors. At each step, some photons get absorbed by the materials or scattered due to imperfections, reducing the system's efficiency. This loss introduces noise, which corrupts the quantum states and leads to calculation errors. For a quantum computer to be functional, it must achieve fault tolerance. Fault tolerance means the system can detect and correct errors, ensuring reliable results even over long computations. Researchers estimate that fault-tolerant quantum computers need error rates below a certain threshold, often requiring a squeezing level of around 9 to 10 decibels to measure how much quantum noise the system can suppress. Optical loss directly impacts this threshold by degrading the quality of quantum states, making it a critical hurdle to overcome. Like the Aurora system described in recent research, current photonic systems experience optical loss at various stages. For example, fiber optic delay lines, which temporarily hold photons during processing, can lose 0.28 decibels of signal due to connectors and splices. This might sound small, but even tiny losses add up in a system with billions of operations, pushing error rates above the fault-tolerant threshold. The GKP approach offers a solution by encoding qubits to make them more resilient to loss and enables efficient error correction. The GKP approach, a game-changer for photonic systems. The GKP approach encodes quantum information in the properties of light waves, specifically their position and momentum. Think of a photon's wave as a grid in a mathematical space, where each point on the grid represents a possible state. GKP encoding places the qubit's information on this grid to make it easier to detect and correct errors caused by optical loss. Unlike other methods that use single photons, which are highly sensitive to loss, GKP uses continuous variable states, essentially the wave-like properties of light, to create more robust qubits. Here's how it works. The GKP method starts by generating special light states called squeezed states, which reduce uncertainty in one property, like position, while increasing it in another, like momentum. Researchers then manipulate these states to create GKP qubits, often using a process called Gaussian boson sampling, GBS. GBS devices produce entangled photon pairs, and detectors herald the creation of non-Gaussian states, which are the building blocks for GKP qubits. These qubits form a lattice structure in the mathematical space, allowing the system to encode information redundantly. This redundancy is key to tackling optical loss. When loss occurs, it shifts the photon's position or momentum slightly, but the GKP lattice structure makes these shifts detectable. Imagine a treasure map with a grid. If someone smudges the map, you can still find the treasure because the grid points help you correct the error. GKP qubits work similarly, enabling the system to measure minor errors and apply corrections without losing quantum information. This error correction capability brings photonic systems closer to the fault-tolerant threshold. Another advantage of the GKP approach lies in its deterministic operations. In quantum computing, deterministic operations always succeed, unlike probabilistic ones that might fail. GKP uses simple components like beam splitters and homodyne detectors, devices that measure light properties at room temperature, to perform logic gates reliably and entangle qubits. Other photonic methods often rely on probabilistic gates, which require extra resources to ensure success. GKP's deterministic nature reduces the system's complexity, making it easier to scale. How GKP enables scalable quantum technology. The GKP approach paves the way for scalable quantum technology by addressing optical loss and enabling fault tolerance. Let's explore how it achieves this through a real-world example. The Aurora system, a photonic quantum computer built with 35 chips. Aurora uses the GKP method to create a cluster-state web of entangled qubits spanning 86.4 billion modes. Researchers entangle GKP bell pairs, which are pairs of qubits encoded using the GKP method, into this cluster state, allowing the system to perform calculations by measuring the photons. Aurora demonstrates several features that make GKP scalable. First, it uses modular design. Each chip handles a specific task, generating, refining, or processing states, and fiber optic cables connect the chips. This modularity means researchers can add more chips to increase the number of qubits, scaling the system without redesigning it entirely. GKP's deterministic operations fit perfectly into this modular framework, ensuring reliable performance across the network. Second, GKP enables efficient error correction. Aurora implements a repetition code, a type of error correction that detects and fixes mistakes in real time. The system runs 13.8 million repetitions of this code, showing it can handle errors dynamically. GKP's lattice encoding makes these corrections possible by clearly identifying errors caused by optical loss. The researchers calculate that Aurora needs a squeezing threshold of 9.75 decibels to achieve fault tolerance, an improvement over previous estimates, thanks to a two-layer error correction system that first identifies errors and then applies a matching algorithm to fix them. Third, GKP tackles optical loss directly. In Aurora, fiber optic delay lines introduce 0.28 decibels of loss, primarily from connectors and splices. The researchers propose a significant improvement by using a single continuous fiber to reduce this to 0.03 decibels, or 0.7% loss. GKP's error correction capabilities complement these hardware improvements, ensuring that even small losses don't derail the computation. By combining better hardware with GKP encoding, photonic systems can approach the fault-tolerant threshold, making them viable for large-scale applications. The future of scalable quantum technology with GKP. The GKP approach positions photonic quantum computers as a leading candidate for scalable quantum technology. Once optical losses drop below the critical threshold, Systems like Aurora could tackle real-world problems that classical computers struggle with. For example, they could simulate complex molecules for drug development, optimize global supply chains, or crack cryptographic codes that protect sensitive data. Photonic's room temperature operation and chip integration also make them practical for widespread deployment. Unlike other quantum systems that require expensive cooling infrastructure, GKP's impact extends beyond hardware. It shifts the focus of quantum computing research toward fault tolerance and scalability, rather than chasing short-term applications with noisy systems. This strategic shift ensures that future quantum computers can run reliable, long-term computations, unlocking their full potential. The modularity of GKP-based systems also opens the door to distributed quantum computing, where multiple photonic systems connect over fiber optic networks to form a global quantum internet. Moreover, GKP's error correction capabilities could inspire advancements in other quantum platforms. Researchers working on superconducting or ion-trap quantum computers might adapt GKP's lattice encoding to improve their error rates, creating a ripple effect across the field. As photonic technology matures, GKP could become the standard for building scalable quantum computers, driving science, medicine, and industry innovation. Why dig deeper? The GKP approach to tackling optical loss in photonic quantum computers is a game-changer, and I encourage you to explore this topic further. Start by reading the Nature article, Scaling and Networking a Modular Photonic Quantum Computer. It's open access and dives into the technical details of the Aurora system. You can also check out books like Quantum Computing, From Linear Algebra to Quantum Programming by Chris Bernhardt, to learn more about quantum principles. Follow the latest research on platforms like Arxiv, or watch lectures from organizations like the Quantum Open Source Foundation. The future of quantum technology is bright. Dive in and see where it takes you. What a fantastic journey we've had today. We've explored how the GKP approach to tackling optical loss in photonic quantum computers can be the future of scalable quantum technology, uncovering how this method makes fault-tolerant, scalable quantum computing possible. From its robust encoding to its role in systems like Aurora, GKP is paving the way for a quantum revolution. I hope this inspires you to dig deeper into this transformative field. What do you think? Will photonic quantum computers change the world? Share your ideas in the comments. I read everyone. Suggest topics for our next video. Give us a like and subscribe to keep exploring with me. Thanks for watching, and I'll see you soon.